So in our sixth installment of differentiation, what we'll be looking at in this video are rates of change. So if you see this word or words used in a particular question, then this video will apply to you. Now this also links in with the mechanics side of looking at SUVAT, which again is something you might want to refer to when you come to learning that topic. So looking at rate of change, so when we have a graph that's on y on x, which is typically what we've had in the past, we can say that the gradient represents the rate of change. So when we've got a graph of y on x, so the gradient of y on x is the rate of increase or decrease of y as x increases. So for example, let's just say that this equation here has a gradient of, let's say, 2x plus 5. Now we can see straight away that the gradient, without having to do dy dx or anything like that, we know that using our knowledge of y equals mx plus c, that the 2 represents the gradient. So what we can say in terms of what the rate of change is for this particular set of data is that y increases at a rate of 2 as for every, I should say, for every increase in x. So it's just another way of us talking about the gradient, but in putting it in terms of words to the common folk. Now, when we are dealing with this, note that y is our subject to the formula. So y is the subject of the formula, and it's in terms of whatever variable is at the bottom. So for example, if I had, let's say, if I hired a plumber, and let's say that the plumber, so let's just write this down, so the plumber charges a standard rate of £50 call out, and he also charges £25 per hour, which I think is not too bad. So the formula for this would be that the total cost is going to be 25h plus 50. So as you can see, this is going to represent a linear function because I've just got a single h, but the rate of change for this is that for every hour, which in other words, for every, because obviously the graph that I would have to represent this data would have h at the bottom because I've got the formula in terms of h, and t is my subject. So again, what would happen here is it'll look like another positive linear curve. So here what I would say is that the rate of change of t is going to be £25 for every increase of h. So as h increases, t will increase at a rate of 25. And it's important that we kind of understand what the graph refers to and what the gradient means, and also relate it to this, what we call rate of change. So as we mentioned, when we've got a graph or a set of axes that's y on x, and the gradient of that curve will be represented by dy over dx, and the derivative of dy over dx therefore represents the rate of change of y with respect to x. Now if we refer to certain graphs and certain formulas that are related more in physics and mechanics, we can also apply this theory as well. So if we look at the first one where we've got speed, so we usually have a graph of distance over time. Now if we were not given a graph, in this case would be given a formula where d is the subject, and what would be on the x-axis would be in terms of. So for this I would have a formula that had d in terms of t, and let's say, just for argument's sake, it'd be represented by this curve here. So this formula would be d equals something t, well in this case it looks like a parabola, so it'd be t squared, etc. So here what we're actually working out is that the speed is going to be equal to, now the gradient, or the formula to work out the speed can be represented by working out the gradient function. So the speed formula is going to be dd, which I'm just going to represent with a capital D rather than lowercase d, so that'd be dd, over dt. So I could work out the speed of any point of this particular graph without having to draw it if I deformed by working out the gradient function of d with respect to t. Now likewise, if I had velocity, so again if I had a graph here, my formula would be s equals something t, and then to work out the velocity, so the velocity formula would be, in this case, either, well, it would be ds over dt, because most cases displacement is represented with the letter s, but again, interpretation of what these would be written in the question. And likewise, if I had acceleration, so let's say we had this as v equals something in terms of t, I would have the acceleration formula would be dv over dt, because I'm looking at the rate of change of v with respect to t. So let's have a look at an example question. So in this particular question, it says that displacement s meters of a body at a time of t seconds is given by the formula of s equals t squared plus 6t. And we've asked to find the velocity of the body at time t, the velocity when t equals 3, and the initial velocity of the body. So looking at question A, this is basically asking me for the formula to calculate velocity. And so sometimes it might give you this, sometimes it might use words like expression. So all I need to do here is differentiate. So for part A, all I need to do is differentiate. So I'm just going to write down the formula again just so that I'm not able to make a silly mistake. So ds over dt is going to equal 2t plus 6, and there is my expression, or the velocity at time t. For part B, so let's just use a different colour. So for B, what I need to do is I need to substitute ds over dt, and I've just remembered I've left out a t there, is going to be equal to, and what I'm going to do here is I'm going to substitute t equals 3 into this formula here. So I'm going to have 2 times 3 plus 6, which equals 12, and there is your final answer. And then finally for C, so again, if I just get a slightly different colour, let's go for this blue. So for C, what I need to do is work out the initial velocity. So that's going to be ds over dt rather, and I'm working out when t equals 0. So here what I'm looking for is going to be substituting 0 in, so I've got 2 times 0 plus 6, which is just going to give me 6. Now in terms of units, which I've not put on here, which really I should have done, is, as you can see, my s is measured in meters. What's gone on there? My s is measured in meters, my time is measured in seconds. So when working out the units for velocity, it's going to be meters per second, or I could write ms to the power of -1. And so it's always worth making sure that you recognize the units, and how I've got the units is because s is measured in meters, time is measured in seconds, and that's where, and because we're dividing, that's why it's either, you can write it as m over s or ms to the power of -1. So looking at this second example, what we've been asked is the displacement s in s meters of a body at time t second is given by the formula of s equals 2t cubed minus t squared plus 2, and we've been asked to find the velocity after 1 second, the acceleration after 1 second, and the time at which the acceleration is 0. So let's have a look at answering this particular question. So with regards to part A, so we know that the formula is going to be given is s equals 2t cubed minus t squared plus t. Then velocity is going to be equal to ds over dt, in which if I now work out the differential function of this, here we get 6t squared minus 2t, and when t equals 1, we've got ds over dt, and I'm substituting t equals 1 into it, we're going to get 6 1 squared minus 2 times 1, which equals 4. And then the units are going to be meters per second, like so. So, and that's after 1 second, which is worth making it after 1 second. So then moving on to part B. Now, in terms of all the formulas, if you refer back to earlier in the video, I gave you a little description about what all the formulas are going to be. So with regards to this, so the acceleration, so for B, that acceleration is equal to dv over dt. Now our V formula is this. So V equals 6t squared minus 2t, and that is what I'm going to be using for this, because I need a formula that's involving V in terms of t. So working out dv over dt, I'm going to get 12t minus 2, and then I need to work out what the acceleration is after 1 second. So I'm going to do dv over dt when t equals 1, and if I substitute 1 into that above formula, I'm going to get 10 meters per second squared. So from this, after 1 second, I should say, it's always worth just reiterating what it is you're actually working for, because obviously using this particular formula, the formula is going to be changing after however many seconds are passing. And again, also worth noting that when we're working acceleration, the units are going to be m meters per second squared. Then moving on to the last part of this particular question. So for part C, so here it's saying work out the time at which the acceleration is going to be equal to 0. So when a equals 0, I'm going to have 12t minus 2 equals 0, and if I go on to solve this, we've got t equals, and it's going to be 2 over 12, which simplifies to give me a sixth, and that's going to be in seconds. So just to reiterate what the actual answer is saying, so we can say that the acceleration when is 0, where t equals 1/6 seconds. And it's always worth understanding what it is we're actually writing in the question, just to summarise, and then we go from there. So hopefully this makes a bit of sense with regards to working out what rates of change are when you see this written in the question. These particular things will probably most likely come up when we look at SUVA and mechanics side of the AS module, but hopefully from this point it makes a little bit of sense to you. If you have any other further questions or would like some practice questions on these, feel free to drop me an email at 162maths@gmail.com.